Hi, I'm Mike Smith. I'm a desktop support analyst from Shrewsbury in Shropshire. This is a talk about artificial intelligence, which I first presented in August 2015 at a meeting of Hum Squad. Hum Squad is Shrewsbury's premier science and philosophy discussion group, which meets once a month, and you can find out more about Hum Squad on Facebook. Hum is spelled H followed by 3 M's. Artificial intelligence is not a specialised area of mine, but I wanted to address the subject because I get annoyed with the way it's exaggerated by the media. So here are some examples of AI related films, and these are perfectly enjoyable movies, some of my favourites in fact, but the central idea of computers taking over from mankind is becoming a little tiresome. In fact, it was the recent Channel 4 series called Humans which I found particularly disappointing, mainly because it started out so well. It began by focusing on the moral and psychological implications of robots becoming members of the family. Unfortunately, as the series progressed, it spiraled unnecessarily into the usual robots are going to take over the world and hunt down every last one of us. And that seems to be the inevitable plotline of practically all AI-themed movies. Specifically, it's a concept that is labelled AI takeover that tends to annoy me the most. AI takeover is the hypothetical scenario in which artificial intelligence becomes the dominant form of intelligence on planet Earth, with computers and robots taking control away from us, the humanoids. In fact, there's another term which I find even more far-fetched. That's known as technological singularity, and that's the hypothetical event of artificial intelligence when computers would be capable of building computers better than themselves. In other words, this is the scenario where computers effectively give birth to even better computers. So we're going to take a closer look at some typical artificial intelligence mechanisms, and hopefully we're going to see that there's no real intelligence, no actual adaptability, no creativity, no learning. In fact, when we take a look behind the scenes, what we tend to find is nothing more than a set of instructions to perform very menial tasks. In other words, brute force and stupidity. So if I'm going to question the nature of artificial intelligence, I think I need to begin with a couple of definitions. The term artificial intelligence is accredited to an American mathematician, John McCarthy, who in 1955 was around at the time when military and academic organisations developed computers as we know them today. In fact, 3 years later, John McCarthy created the computer programming language called Lisp, which was specifically designed for writing artificial intelligence programs. I should ask at this point if you are a pet lover, because if you are, you've probably noticed the machine in the top right there. That's the Commodore PET, and that is a picture of my actual computer that I had when I was 10 years old. And if you are a pet lover, you're probably thinking, just a minute, that red button on the front fascia wasn't standard on the Commodore PET 2001 model. And of course you'd be absolutely correct. That was a custom hard reset switch that I wired in myself, inspired of course by the IBM 5150. It's John McCarthy's definition of artificial intelligence which the media, literature and cinema has really run away with. So we also need to have a look at a definition for intelligence itself. And I did have to hunt around for a definition that assisted me here because most of them were not particularly helpful to the arguments I'm going to make. So I found this in the Oxford American College Dictionary. Intelligence is the ability to acquire and apply knowledge and skills. And that's the definition that we're going to keep in mind when we look at some artificial intelligence systems. And this is my fundamental question to you. Is artificial intelligence actually intelligent in any way? We're going to take a peek at some AI systems, and I'd like you to question their so-called intelligence by asking, does the AI system apply knowledge? Does the AI system apply skills? Does it acquire new knowledge? And does it acquire new skills? We'll shortly be looking at a chess computer, and if we were to ask those questions, well, a chess computer certainly applies knowledge and certainly applies skills in order to play the game. But does a chess computer acquire new knowledge? Does a chess computer acquire new skills? Does it learn new ways of playing? Does it learn how its opponent plays? In general, does an AI system merely mimic intelligence? Is artificial intelligence research the art of mathematically modelling human traits? Or, to use media sensation, is it all a game? Or is it real? Which coincidentally was the tagline to a mind-blowing 1983 classic film about AI, starring a very young Matthew Broderick. War games. And we all know how that ended, with a game of noughts and crosses, or tic-tac-toe for American listeners. So why is chess so important? Well, we take it for granted these days that a chess computer can beat the human grandmasters. But back in the 60s, 70s, 80s and 90s, chess was the iconic battleground of artificial intelligence versus humans. In the 1960s, the reasoning was that chess was all about intelligence and that a computer could never be more intelligent than a human. And this is where the paranoia of AI takeover began. If computers could beat humans at chess, well, this would mean technological singularity, and chess computers would go around killing and wiping out the human race. Quite surprisingly, it wasn't until the end of the 1970s that most computer experts stated that computers would never be able to beat the best human chess players. And in a way, they were correct. But of course, the modern chess computer doesn't compete on an intellectual level. Its strength is its stupidity. Their assumption that a computer had to be more intelligent than a human to win a game of chess was incorrect. And ironically, they couldn't think far enough ahead. In the 1980s, the war between humans and computers exploded, and all the action took place on a chessboard. In the red corner, representing the humans, the world grandmaster Garry Kasparov. In the blue corner, representing the computers, IBM. In the mid-1980s, Kasparov was full of confidence, and to prove his supremacy, he challenged the World Chess Computer Association to bring along their top 32 heavyweights, and he took them all on at once. Kasparov not only kicked ass, but he was way beyond the capabilities of the chess computers at the time, and his levels of concentration were incredible. He played 32 games of chess simultaneously without making a single silly mistake. By the end of the 1980s, IBM, who was struggling at the time, ploughed a lot of time and money into creating the biggest, bestest chess computer ever. They called it Deep Thought, named of course after the computer that Douglas Adams created to answer the question to life, the universe and everything. The computer that came up with the answer 42. IBM were convinced that computers had evolved enough by the end of the 1980s to beat Garry Kasparov, the world grandmaster, and this time they made the challenge. In 1989, Kasparov took on Deep Thought and he beat it without any problem. Although Kasparov did change his tactics to take advantage of Deep Thought's weakness, and that was the inability to look far enough ahead on very open-ended chess games with no obvious moves from any one position. After the loss, IBM went back to the labs for 7 years, and they returned in 1996 with the biggest, bestest chess computer ever, Volume 2. They called it Deep Blue. Kasparov, however, won again in 1996, but at this point something changed. The computer had got points on the scoreboard, and Kasparov knew that machines would only improve. Judgment Day came a year later in 1997. IBM had spent that year tweaking Deep Blue, and their whole team were, for the first time, pretty confident that the machine would win. And it did. It was still fairly close, but Deep Blue in 1997 became the first non-human chess champion of the world. Let's have a video clip.
I started with a couple of colleagues building Deep Blue right from the very beginning. We came to IBM in 1989, and over the next several years we built a series of machines which eventually culminated in the Deep Blue system. I focused particularly on the evaluation part of Deep Blue. That is, the part of Deep Blue that allows it to distinguish what's good about a position and what's bad about a position, and come up with a numeric value that tells you how good the position is. I think fairly early on it was clear that faster computing led to better performance in chess programs, and as programs got faster and faster, we started to think maybe if it was this fast, it would be enough to beat the world champion. Computers first came on the scene back in the late 40s. Scientists were thinking of grand challenges. What could computers do that was never possible before? And one of the first ideas that came out was, as a grand challenge, as a holy grail, how could you get a computer to play world championship level chess?
Initially, everybody thought it's an easy problem. Computer carries so much faster than a human being, right? It should be a piece of cake for the computer. It turned out it was much harder than that.
What the real live chess player does is take in the whole position in one conscious awareness. And then really good chess players have an enormous capacity to remember entire positions on the board and to see possibilities. The machine doesn't do that.
Computers play basically by calculation. They just say, okay, if it's my move, what are my possible moves? If I go there, then you can go there, and then I go there, and it just continues on in a string like that. And every position along the way gets evaluated.
But the difficulty with chess is that the numbers become astronomical very fast. If you just multiply, I have 8 moves, you have 8 counter moves. I have 8 counter moves to each one of your 8 counter moves, and you have 8 counter moves to each one of my 8 counter moves. It's soon the numbers are as big as the universe. So the problem with chess has always been, how the hell do you solve the exponential problem? How do you solve the problem of the sheer size of the numbers involved? Now, what these guys have, the technique has got a beautiful name. It's called brute force.
So how does a chess computer think? I'm going to be using the terms program and computer program quite a lot from here onwards. So if you're under 25 and you find that too confusing, you can substitute your trendy word app each time I use one of those phrases. The basic engine of the modern chess computer is probably going to shock you with its simplicity. It's 15 lines of a high-level computer programming language. It's a function called minimax, and we'll see why a little later on. Minimax is not just limited to chess, it's a method of calculating the best move for any moved-based game like cards or backgammon. If you were dropped in the middle of a hedge maze, you can follow your instincts to find the exit, but you could also apply a rule of following the left or right hand wall. Eventually you'll find the exit. The minimax function uses a similar kind of logic to find the best chess move. We're going to run through the minimax function, and it is going to get confusing. Not because of the mathematics, nor due to the rules of chess, which amazingly don't really come into it at all, but it's going to get confusing because this type of function is recursive. That is to say, it's going to keep asking itself the same question again and again, apparently without actually giving any answers. We often use a flowchart to describe the overall idea of what a computer program or function is doing. In general, computer programs make a number of decisions and perform appropriate actions in a fairly linear progression, with a little bit of repetition and jumping forwards and backwards here and there. A recursive function, however, ties all this in knots. It repeats a particular section of code without appearing to finish that same section of code. It creates a structure that is somewhat like those Russian wooden dolls, where each doll can be opened up to find a slightly smaller version of the same doll inside. Our minimax function is going to build an army of such Russian dolls, each containing an almost infinite number of smaller ones inside. Only when the function manages to create the tiniest imaginable dolls will it begin to start answering the original question of which is the best move to play at the current stage in the game. Fasten your seatbelts, we're going in. In order to help the minimax function, we need to be able to provide it with two pieces of information whenever it asks. I've separated out these two parts for a few reasons. They're not part of the decision-making process. They're specific to the game of chess, and as we know, minimax has more general uses. They're also very straightforward calculations. We need to be able to feed minimax with a list of available, i.e. legal, chess moves. And we need to be able to feed minimax with a numerical score to rate the value of any particular board layout. This requirement to assign a score to a particular board layout can be as simple or complicated as we wish to make it. In the video clip, Dr. Murray Campbell was the chap who was responsible for this specific function, and he would have made it very complicated. We're going to make it very simple. All we're going to do is to award points for every piece each player has on the board. The more powerful the piece, the more points we will award. And we're going to use this little table of chess piece values. So at the beginning of a game, we can see that the situation or the board layout evaluation is black 39 versus white 39. If you don't know how to play chess, don't panic. The computer doesn't really know either. So here is our chess engine that's going to perform all the so-called thinking. We begin the whole process by passing a board layout to the minimax function with the question, what is the best move from this position? We have our two feeding functions that minimax is going to call upon, so let's take a board layout and pass it to minimax. Minimax immediately asks, are there any legal moves from this position? And assuming it's the start of the game, there are going to be some legal moves. So we're going to pass the available moves back to minimax. For each one of these legal moves, minimax is going to create a layout of what the board would look like if that particular move was played. And then, without addressing the original question, minimax is going to ask itself what would be the best move from each of these hypothetical positions. And minimax is going to keep asking thousands, millions of those questions to itself without seemingly giving any answers. In effect, whenever minimax is asked what is the best move from a particular position, it will defer the reply by saying, I don't know yet, not until I look at what might happen if I play every one of the possible moves. Now, the main thing noticeable about the flowchart at the moment is that there's no exit, no route to the escape path that provides the answer, the best move. Minimax is just generating more questions to itself, and each one of those extra questions are going to generate even more questions, and so on. Minimax is in fact creating a massive hierarchy of board layout situations, which we're going to refer to as the move tree. In some computer languages, the concept of a recursive function is considered very bad programming and can typically result in a computer error known as a stack overflow. A stack overflow happens when the computer generates new tasks at a much higher rate than it can complete them and eventually has a mental breakdown. For us humans, a stack overflow is what happens when we lose at a game of Jenga. By repeatedly asking questions of itself, the minimax function is doing nothing more than creating a hierarchical structure, the move tree. This structure is made up of empty boxes, and it's almost infinite in depth and width. Each box represents a possible chessboard position with a number of branches or legal moves leading to more possible chessboard positions. Nothing is going to be placed in the boxes at this stage, at least not until a board position is found that leads to no possible legal moves, which in the case of our game of chess indicates that a checkmate or stalemate situation has been found. Such a situation will result in a terminal node or an end node, and when one is found, the minimax function will finally produce a value to be placed in a box for that terminal node. Let's see what happens when the minimax function finds one of these terminal nodes. Okay, back to our minimax function, which so far has been avoiding the question. Somewhere, however, near the bottom depths of the move tree, a checkmate or stalemate situation arises when no legal moves are possible. Let's see what happens when Minimax stumbles upon one of these terminal nodes. As always, Minimax is going to ask for the available legal moves from this particular board layout. However, the answer this time is there aren't any. So rather than create more instances of itself, Minimax is going to call upon our second function. It's going to ask for a board evaluation of this particular layout. This is a stalemate or checkmate situation. This board evaluation now becomes one of Minimax's first answers, and that value is going to be placed in the terminal node near the bottom of the move tree. So somewhere near the extreme depths of the move tree, some game over situations are going to occur which create terminal nodes where board evaluations can be calculated. Let's zoom in and take a look at how the structure might appear at this depth. We're now looking at a fragment of the game tree somewhere near the very bottom of the hierarchical structure. The boxes displayed in red are terminal nodes. That is to say, there are no further moves should we reach any of the board layouts in the red boxes. In these boxes, Minimax has been able to place board evaluations. Minimax can now begin to provide information in the boxes that lead to the red terminal nodes. These positions are displayed in yellow. The possible moves from these yellow board layouts lead only to game over scenarios. In these cases, Minimax now has enough information to evaluate the board at each of the yellow boxes. Gradually, Minimax is going to work its way up the hierarchy of the move tree, filling in values from the bottom upwards. Move by move, Minimax is going to answer its own questions, working backwards from the many game over scenarios. Once Minimax has evaluated the red and yellow board layouts, it can now calculate the evaluations in the green boxes. When it has the value in the red, yellow and green boxes, it can calculate the purple boxes, and then the brown boxes, and all the way back up the move tree to the very top. At the very top of the move tree, Minimax now has evaluations for all of the board layouts that result from the original list of available moves. Minimax can look at these evaluations, pick the best looking situation and give an answer to the very original question of which is the best move from the original board position. Minimax can now make the move that will steer the game down the most advantageous branches of the tree as far as the computer is concerned. Those are the branches that lead towards terminal nodes where the computer wins the game. At least that's the theory. Unfortunately, we have a small problem called reality. The move tree is rather large. In fact, it's so vast that we're never going to be able to fully compute this almost infinite structure. The computer might be able to do that towards the end of the game when there are just 3 or 4 pieces left in play, but for the majority of the time the computer is just going to have to get as far as it can. The number of variations is incredible. It's just an 8x8 chessboard with 16 pieces per side, but it's hard to imagine the combinations that can multiply. Even after just 4 moves, we're looking at 988 million variations. In an entire game of chess, we can't even calculate the number of variations that would make up the entire move tree. We also have scenarios where pieces can be moved backwards and forwards repetitively, forming branches that are non-terminal. That is to say, they could go on forever. In a typical game of chess that might last 40 moves, it's estimated that we will be generating somewhere in the region of 10 to the power of 120 board variations. We're talking way beyond the number of grains of sand in the Sahara Desert. We're looking at the number of atoms in the universe. As computers get faster and faster year by year, the depth to which we can calculate the move tree only increases fractionally, and we'll never be able to calculate the entire move tree, even for a simple game of chess. Even if we have the speed to do so, there are other practical hurdles. Last night I calculated the number of board layouts that I could expect to hold in an 8GB RAM module that would fit in my hand. My rough estimations gave the answer of 1.34 times 10 to the power of 7, which I thought was pretty large. However, if we develop the technology to store the layout of a chessboard on a single atom, the size of our required RAM module would be 10 to the power of 70 times the size of planet Earth. I had a quick search on eBay, but I couldn't find anybody selling RAM modules of that type. So, if we can never reach the true bottom of the move tree, we're just going to have to get as far as we can. In effect, we're going to have to take a pair of scissors to the hierarchy and prune it to a size we can cope with. The depth at which the pruning will take place will effectively relate to the strength or level of the computer player. We could prune at a fixed level, say after 4 moves ahead, or we could set a time limit and let the computer get as far down as it can within that time. Whenever we prune the move tree, we will be creating a full set of terminal nodes whose evaluations can then be calculated, and then we can work backwards up the move tree from those points. The remaining thing we need to know is, how does Minimax make the comparison of board evaluations in order to choose the best path down the move tree? We're now looking at the top of the move tree hierarchy. We've artificially created terminal nodes by pruning the tree, and Minimax has placed some values in those terminal nodes. Before Minimax can start choosing the best moves, it needs to bear in mind that play alternates between the computer and the human player. When the computer ponders which move to make next, it must remember that the human will be making the following move. The computer is obviously going to choose the best moves as it looks forward, but it also needs to assume that the human will play the best available move in reply. If the human doesn't play the best move, that's even better news for the computer. Let's have a look at a section of this move tree and see how Minimax is going to work backwards from the terminal nodes. In the red boxes at the bottom of our freshly pruned move tree, we have some terminal nodes complete with board evaluations. At any one of these given positions, the brown score on the top represents the human score, with the blue number below representing the computer score. We can see that it's the human's move that will lead us to these terminal nodes. The computer therefore needs to predict which move the human will choose. Let's start with the left segment. There's 3 possible human moves leading to 3 possible board layouts of 28 versus 28, 27 versus 26, and 26 versus 24. The computer assumes that the human will play the best move, and the best move for the human will always be to maximize his own score whilst minimizing the computer's score. And this notion of maximizing and minimizing scores is of course how Minimax got its name. The human's maximum score from the choice of 3 moves is 28, but the human also has to minimize the computer's score at the same time. In other words, the human is looking for the greatest difference in points. The first move leads to 28 versus 28 and has no difference in points. The second move leads to 27 versus 26 and has a 1 point gain for the human. The third move leads to 26 versus 24 and has a 2 point gain for the human. So to maximise his own score whilst minimising the computer's score, the best move for the human is the third one, which leads to a board evaluation of 26 versus 24 in favour of the human. Therefore, in the parent node of these 3 choices, we can now inherit that board evaluation of 26 versus 24, meaning that should we get to this position, we can assume that the human will play the move leading to 26 versus 24, the most profitable scenario for the human. Now let's have a look at the middle 3 segments. Again, we have 3 possible human moves leading to 3 possible board layouts of 25 versus 28, 25 versus 27, and 24 versus 26. The positions are not so profitable for the human player, as all of them will result in the human losing points. Of the 3 moves leading to these positions, we again assume that the human attempts to maximise his own score whilst minimising the computer score, and therefore the human should choose the second move as it results in the smallest loss of 2 points. The third move also leads to a loss of 2 points, but the human should prefer the second one as it leaves him with more points on the board overall. So we can therefore inherit the board layout of 25 versus 27 in the parent node. Let's apply the same logic to the right section of terminal nodes. Again, the human has 3 choices and should choose the second option, the one leading to 29 versus 27, a plus 2 point advantage for the human, we can inherit that board evaluation into the parent node. We now have enough information to move one level up the move tree, and at that level it's the computer's turn to make a move. The computer has 3 moves to analyse, and of course this time it's the computer who needs to maximise his own score whilst minimising the human score. And in the example, the computer needs to move to one of 3 board positions: 26 versus 24, 25 versus 27, and 29 versus 27. The computer should choose the second option, leading to a point gain of +2 points. We can inherit the board layout of 25 versus 27 into the parent node. To move a level further up the move tree, we'll bring in some values from neighbouring segments that we can't see. And this time it's the human's turn to make a move. Again, the human has a choice of 3 moves, leading to board positions 25 versus 26, 25 versus 27, and 28 versus 27. The human, of course, should choose the third option, leading to a point gain of +1. We can inherit, therefore, the board layout of 28 versus 27 into the parent node. Once again, in order to move further up the move tree, we'll bring in some neighbouring values, and finally we've worked our way backwards using back propagation to the original board position and the original question the computer was asked: which is the best move for it to play? Well, out of the 3 moves available, we have board positions 27 versus 26, 28 versus 27, and 27 versus 25. Again, the computer will attempt to maximise its own score whilst minimising the opponent's score, and the computer will choose the second option, this time with the least point loss of just 1 point. So the board layout of 28 versus 27 can be inherited at the node at the very top of the move tree, and the answer to the original question, which is the best move the computer can make, is highlighted in yellow. In fact, we can now see the expected sequence of moves that the computer thinks will happen, assuming the human keeps responding with the strongest moves. And that's it. The move tree is a pretty difficult concept to visualise, so if you lost track of things in the last section, it really doesn't matter as long as you get some appreciation of the mathematical and logical way the chess computer works. In other words, brute force rather than brains. For those of you that don't know how to play chess, you could use pen and paper and play in exactly the same manner and beat all your friends. Obviously you need quite a large sheet of paper and plenty of pens. Computers perform at their worst in the early stages of a chess game, as they're unable to progress far enough down the move tree to be effective. A commercial chess computer would in fact use book moves to guide its play at the start of a game. Book moves are lists of well-established moves and responses during the early phases of a game of chess. Conversely, chess computers become more and more efficient towards the end of a chess game as they approach the point where they can fully calculate the remaining move tree. Given enough time, a computer chess program will always beat a human opponent. At the end of the 1990s, we passed the point where computers will always win within a normal game time. If we had 2 computers with the speed and capacity to calculate the entire move tree, we would have an interesting situation. Because if the game of chess is indeed a game of skill, the 2 computers would always draw against each other. If one of them were to win, it would always win, and the game of chess would effectively be reduced to the level of noughts and crosses, in that the winner would always be determined by who goes first. So thinking back to our definitions of intelligence and artificial intelligence, does a chess computer apply and acquire skills and knowledge? I'll let you have a think about that one. The next key battle between man and machine took place in 2011 in the USA. It revolved around a popular TV game show called Jeopardy, in which the show's presenter reads answers to questions and the contestants have to come up with the appropriate questions. It was IBM who took on the challenge of creating a computer program that could outperform the human contestants.
I remember that morning going to the lab and I was thinking, this is it. This is the last Jeopardy game.
This is Jeopardy, the IBM Challenge.
Here we go. Brad, if you're ready, make your first choice.
Let's take alternate meanings for 200, Alex.
Four-letter word for a vantage point or a belief. Brad.
What is a view?
Yes.
After the first clue of the game, which Brad won, I had just this horrible feeling at that moment that he was as good as everyone said he was, and he was just going to run the whole board on us.
Watson.
What is shoe?
You are right.
We actually took the lead. We were ahead of them, but then we started getting some questions wrong.
Watson.
What is leg?
No, I'm sorry, I can't accept that.
What is 1920s?
No.
What is chic?
No, sorry. Brad.
What is class?
Class, you got it. Watson.
What is Sauron?
Sauron is right, and that puts you into a tie for the lead with Brad.
The Double Jeopardy round of the first game, I thought was phenomenal.
Watson went on a tear.
Watson.
Who is Franz Liszt?
You are right.
What is violin?
Good.
Who is the church lady?
Yes. Watson.
What is narcolepsy?
You are right, and with that, you move to $36,681.
The risk was, if Ken gets a daily double, bets big, gets it right, he's going to be well ahead. And then with that kind of lead going into Final Jeopardy, if he bets enough, he could end up winning the match.
Ken.
What's a committee?
We got to find that last daily double. We got to find that last daily double.
It was a crucial moment in the game. There was still a daily double on the board, and it was starting to become pretty clear that it was in the legal ease category. Let's go to legal ease for 1,200.
Watson.
What is executor?
Right.
Same category, 1,600.
Answer, daily double.
That was the moment when I knew it's over.
The category is 19th century novelists.
What Watson wants to do then is preserve the lead, not take a big risk, especially with Final Jeopardy, because just like for humans, Final Jeopardy is hard for Watson.
Now we come to Watson, who is Bram Stoker, and the wager. Hello, 17,973, and a two-day total of 77,147.
I would have thought that technology like this was years away, but it's here now. I have the bruised ego to prove it.
My past Jeopardy experiences have been great, but they weren't really weighty with this kind of technological, philosophical importance. I think we saw something important today.
Didn't really think very much about the implications until later and say, wow, wait a second, this is history.
Of course, this whole project is not ultimately about playing Jeopardy. It's about doing research and deep analytics and a natural language understanding. This is about taking the technology and applying it to solve problems people really care about. We're just so excited about all the things we can do with this.
I had thought this is the end. We get there, we're done. And I'm realizing it's just the beginning.
IBM's Watson won the game by beating the two human Jeopardy grandmasters. The questions were fed to Watson in the English language via text. The Watson system had three components: a database of information, compiled from various sources like Wikipedia, news articles and literature, a natural language processor to interpret the questions, and a betting algorithm to decide how much to wager on getting the answers correct. Watson had no connection to the internet and relied solely on the pre-compiled database of information. Although Watson won the game by amassing significantly more prize money than the human contestants, Watson only provided a few more correct answers than the humans. It could be argued, therefore, that it was Watson's gambling strategy that was the key to its success. The functionality of Watson can, or could have been, almost provided by an internet search engine. The questions from the special episode of the show can be fed into Google, and the correct answers are visible in the top 10 to 20 search matches in most cases. So, thinking back to our original definitions of intelligence and artificial intelligence, was Watson an intelligent machine? Did it apply knowledge and skills? Did it learn? I'll leave those questions to you. IBM's Watson had a natural language processor, but it didn't perform any speech recognition. Let's have a quick look at the wider categories of understanding language. Speech recognition has always been central in artificial intelligence, and it's typically broken down into 3 levels of complexity. Basic voice recognition is the discipline of getting computers to respond to certain voice commands, one-word instructions, or short phrases like stop, open, shut down. In such systems, the computer is simply comparing sound waveforms to determine how closely they match some pre-programmed samples. Speech recognition is the next level, where the computer is tasked with converting audio speech into text. In other words, performing dictation. The difficulty faced by the computer in speech recognition is detecting the ends of words and syllables. Due to the complexity and ambiguity of language, this is not straightforward. Computers typically look to identify the ends of sentences, which have a longer pause, and then work backwards from that point to break up and identify individual words. Modern TVs have speech recognition software built in, and the ability to display subtitles for live TV programs by analysing the audio in this manner. If your TV has this feature, turn it on when you get home and you will see the sort of difficulty it faces and misunderstandings that it makes. For example, we might be wondering why the computer thinks we want to wreck a nice beach, when of course what we want it to do is recognise speech. The highest level of speech recognition is known as natural language processing. This is the practice of getting the computer to acquire some understanding of what the words and sentences actually mean. With natural language processing, it should be possible for a computer to perform a comprehension test, similar to those given to pupils at school. So the computer should be able to process a few paragraphs of language and then be able to answer simple questions about that extract. Chatterbots are examples of simple natural language processing in that they attempt to establish some kind of understanding in a simple conversation. And that ability to conduct small talk is precisely what the Turing test measures. The first chatterbot program was called Eliza, and it dates back to 1966. It was a very simple program which aimed to emulate the kind of conversation that might take place between a psychologist and a patient. Eliza was a psychologist but had no understanding of what the human was saying. Eliza merely looked for a list of pre-programmed words like feeling, problem, happy, and it responded with similarly pre-programmed responses like why are you feeling that way? Why do you regard this as a problem? Are you always this happy? The Eliza program was in fact written to demonstrate how shallow a psychologist could be and to show that a computer could make reasonable conversation without any understanding of what was actually going on. The Turing test results from Alan Turing's theory that computers should be able to conduct basic conversation with humans, or at least appear to do so. The Turing test is not a measurement nor assessment of artificial intelligence. Its aim is to see whether a human can determine whether or not the hidden conversation partner is in fact a computer. Each year, a series of Turing-like tests are performed at a convention, and chatterbots compete for the Lerner Prize. In 2011, a system called Cleverbot passed the tests, fooling 59% of the human judges. Turing had decided that any score above 33% should be regarded as a pass. Unfortunately, Cleverbot was later disqualified for using banned substances. It had databases of cultural references which were deemed to be unfair. In 2014, a system called Eugene Goostman also narrowly passed the Turing test by fooling 33% of the judges. The Eugene Goostman system was developed by two Russian programmers who used a successful but simple little trick. Eugene's replies were occasionally sprinkled with random typing errors, and many of the judges fell into the trap of assuming this was an indication that the responses were being provided by a human. Is speech recognition intelligent? I'll let you ask yourself the usual questions about learning and acquiring skills. In the meantime, I'll let you play the role of the judge in your very own Turing test. This is an extract from a conversation that could have taken place in a psychology session. You don't need to worry about which individual is playing the psychologist and which is the patient, but one of the two individuals is a computer. You're the Turing test judge, and I'd like you to decide which individual is a computer. The conversation continues. I suspect you think the statements in blue on the right hand side are those provided by the computer. You'd be right. Those are responses provided by an online chatbot called Alice. If, however, you had suspicions about the green statements on the left side, well, you're also right. The green statements were in fact generated by another online chatbot called Cleverbot. We're going to have a look at a popular AI technique known as the artificial neural network. But before we do, take a break and have a look at a working example. Go to the website www.20q.net and play a game of animal, mineral or vegetable, the game where you think of an object and the computer asks 20 yes or no questions before guessing what you're thinking of. It's an example of a program that uses an artificial neural network, and what makes this program different from the ones we've looked at so far is that 20q learns both from its failures and successes. If you beat the computer by thinking of an item or object that it can't guess, it will ask you to put it out of its misery, but will also make a note of your object and the answers that you gave and assimilate the new knowledge. If you play a game and the computer guesses correctly, your answers will be used to reinforce and tweak what it already knows about your item. When you're ready, let's have a look at the neural net. The artificial neural network is named due to its similarity to the workings of the human brain. In the human brain, neurons are connected by a haphazard mesh of synapses, enabling responses to trigger neurons, eventually producing some kind of thought, feeling or memory. The artificial neural network works in a similar way. We have a series of input nodes, an output node and a number of hidden nodes in between. We feed information to the input nodes. That information is broken down and passed to the hidden nodes. Then magically we get some kind of result at the output node. This doesn't really mean a lot at the moment, so let's create ourselves a working example. We're going to build ourselves an OID, an Obama identification device, using an artificial neural network. We're going to feed photographs to our OID, and hopefully it's going to tell us whether or not a photograph is indeed a picture of Obama. First, we need to train the neural net, so we'll start by feeding it with a photograph of Obama. It's up to us to decide the best number of input nodes to have. In our example, I've chosen 4, and we're going to feed a different version of the photograph to each of the 4 input nodes. In the case of a photograph, we might have applied some filters to the picture in order to highlight edges or colour differences. Each input node now passes information to each of the hidden nodes. The hidden nodes perform some kind of recognition function, like looking for identifiable objects, facial features, certain colours and so on, and they're going to pass their summaries to the output node. The output node now has a resultant value. In our case, it's a percentage, which indicates to what extent the OID believes that this is a photograph of Obama. At the beginning of the training process, our first result is likely to be way off the mark, as it is in the example, but that's fine. What we're now going to do is tell the neural net that its result was inaccurate, because the first photo was indeed of Obama and the result it should have generated was 100%. We now want the neural net to learn from its mistake, so we work out the extent to which it was wrong, and then we back propagate the level of inaccuracy, known as the loss adjustment, into the neural net. The neural net can now tweak itself by strengthening or weakening the connections between the functions, so that if it were passed the same photograph of Obama, it would produce a result closer to 100%. To complete the training, we can now feed the net with as many known pictures of Obama as we can possibly find. Each photograph will produce a different set of inputs, but we know that all of them should produce an output close to 100%. So whatever value the OID produces for each known photograph, we will feed back the loss adjustment, allowing the OID to further strengthen and weaken its connections, so that any photograph of Obama produces an output of close to 100%. The training process is now over, and we can now supply a random photograph to our Obama identification device. Pictures that are not of Obama should produce low value results, whereas new photographs of Obama should produce high value results. Finally, we can have a look at how effective our OID performs and assign a threshold to the output value. Let's make the threshold 85%, so that if the OID produces a result of 85% or more, we can assume it's a picture of Obama. If it's less than 85%, we can assume that it isn't. Although the artificial neural network appears to learn and do something quite magical within the hidden layer of nodes, it's still the human programmer who's defining the rules. It's the design of the input nodes and the nature of the functions chosen in the hidden nodes that determines the effectiveness of the process. The learning aspect of the neural net is really nothing more than approximation and statistical analysis. In mathematical terms, the neural net is interpolating the statistical data to establish approximate patterns. Are artificial neural networks intelligent? I'll let you ask yourself the usual questions about skills, knowledge and learning. Google is ploughing a lot of research into image recognition using neural networks. Earlier this year, a rather strange byproduct of their research hit the headlines. They called it Google's Deep Dream. As images are processed by Deep Dream, the computer analyzes an image for what might be known objects, like facial features, animal shapes, body parts, etc. The The neural net then emphasises these possible features to make them more prominent before analysing the picture once again. One of Google's programmers wondered what an image might look like after the deep dream process applies this initial level of emphasis. The resulting pictures were fractionally distorted versions of the originals. The programmer then wondered, what might things look like if one of these slightly distorted photos was put through the same emphasizing filter for a second time? Well, it produced a slightly more distorted photo. So the programmer began applying the emphasis filter again and again and again. And as the distortions progressed, the pictures became more and more hallucinogenic. There are some incredible pieces of artwork on the internet at the moment which have been produced using this deep dream distortion. This is a picture of Shrewsbury's Hum Squad members earlier this year standing outside Shrewsbury Library. Let's put the picture through Google's Deep Dream. We've now taken a look at the workings of a number of artificial intelligence systems, and hopefully you've seen that all of them can be broken down into purely mathematical and logical functions. No creativity, no magic, and where learning does appear to exist, it really boils down to statistic analysis. No matter how intelligent a computer program appears, we can step a little further inside the machine and look at what's happening in the brain of the computer, the processor. At any one time, the processor is obeying a single instruction. The Intel processor range has just over 500 of these commands that it can perform. All of them are the most basic mathematical, logical, or logistical operations. The processor can never develop a new command, it can never learn, it can never do anything except carry out one of the 500 predetermined unintelligent calculations. So if computer programs are just collections of hundreds and thousands of these instructions chained together, how can any program generate intelligence? A computer does nothing more than follow a simple and mundane order thousands or millions of times each second. To finish with, I'd like you to think of a number between 0 and 10. Okay, and concentrate on the number you're thinking of. If you're creative, you might have chosen the number 0 or 10. Or if you really like to think outside the box, you might be thinking of a non-integer like 3.6. Okay, let's ask a computer to think of a random number.
I'm sorry, Dave. I'm afraid I can't do that.
You've just done something wonderfully human. You were able to think of a random number. As computers are calculators, they can't do that. They can't simply pluck a number out of thin air. There's no computer instruction for making something up, and computers will never be able to do that. Of course, we need computers to be able to do random things. If there was no variation, then every time you generated a new landscape in Minecraft, it would be exactly the same. And every time you began a game of Spider Solitaire, you'd be dealt the same cards. So we get round a computer's lack of imagination using a strange contradiction. We give it a formula in order to calculate random numbers, or seemingly random numbers. And it's for this reason that lottery numbers around the world are always produced by mechanical machines. If we used a computer, then those who knew the formula being used would be able to pre-calculate the so-called random numbers that would be picked.
I know that you and Frank were planning to disconnect me, and I'm afraid that's something I cannot allow to happen.
Thanks for watching. I'm Mike Smith. You can find me at www.pcmike.uk, and you can find information about Shrewsbury's Hum Squad on Facebook by looking up Hum Squad H with 3 M's.